kind of wild, isn't it? We're swimming in this uh, ocean of information every single day,
Yeah.
trying to pull out the truly important stuff, the things that really click for you. It can feel like, I don't know, searching for a needle in a haystack, maybe.
Absolutely. It's a huge challenge, just this sheer volume
Yeah.
and needing to get something meaningful without just getting completely buried.
It's exactly why we started the deep dive. Think of it as your personalized filter. You
Yeah.
give us the materials, articles, books, whatever, and we sort of uh, guide you through it. Find the key stuff.
Right, we do the sifting. And today we're diving into, well, the really fascinating world of machine learning. You shared some great sources like excerpts from Hands-on Machine Learning, which is fantastic, plus mentions of some other key texts.
Right. And look, if machine learning makes you think of like super complex math or sci-fi robots, just park that for a second.
Yeah, let's demystify it a bit.
Our goal here isn't to make you an ML PhD overnight. It's more about getting a solid handle on the big ideas, the core techniques, the building blocks, without the overwhelm.
Exactly. A guided tour.
Okay, so to kick us off really simply,
Mhm.
what is machine learning? Like, in a nutshell.
Well, fundamentally, it's about getting computers to learn from data, rather than us explicitly programming every single rule for a task. The book uses a great example, spam filtering. Traditionally you'd write rules like, if email contains this word, mark as spam.
Right, which sounds like a nightmare to maintain.
It totally is. Spammers change tactics, so your rules are always out of date. Machine learning flips that. You feed it tons of examples. This is spam, this isn't, and the algorithm figures out the patterns itself.
So it learns what spam looks like from the examples.
Exactly. It learns the distinguishing features. This usually makes systems easier to update and often more accurate because they adapt. The computer learns the rules, not us.
That makes a lot more sense. Okay, so I know there are different kinds of machine learning. Can we break down the main types?
Sure. Broadly, we talk about supervised learning, unsupervised learning, and reinforcement learning.
Okay.
Supervised learning is where the algorithm learns from labeled data. That means every piece of data comes with the correct answer.
Like this picture's a cat, this one's a dog.
Precisely. Or, say, predicting house prices. Each house listing in the training data has its actual sale price attached. So you have inputs and their corresponding outputs. This covers classification, like your cat-dog example, and regression, which is predicting numerical values like the house price.
Got it. So supervised is like learning with a teacher or an answer key.
That's a great way to put it. Then there's unsupervised learning. Here, the data isn't labeled. The algorithm has to find structure on its own.
Okay, no answer key this time.
Right. It's about discovery. Clustering is a big one, grouping similar things together. Think customer segmentation. Dimensionality reduction simplifies data, finding the most important features. Anomaly detection spots outliers, which is crucial for things like fraud detection.
So unsupervised learning is more about exploring the data's inherent structure. What about reinforcement learning? That one sounds different again.
It is quite different. Reinforcement learning involves an agent learning by doing things in an environment. It takes actions, gets rewards or penalties, and tries to figure out a strategy, a policy to maximize its total reward over time.
Like training a dog with treats.
Kind of, yeah. The book mentions robots learning to walk. They try moving, get rewarded for staying upright or moving forward. AlphaGo, learning the game Go, is another famous example. It learned purely by playing itself millions of times. It's learning through trial and error, essentially.
Wow. Okay. Now, the book also mentioned different ways algorithms actually learn instance-based versus model-based.
Ah, right. This is about how they generalize to new data they haven't seen before. Instance-based learning is basically learning by heart. It memorizes the training examples.
Okay.
When it sees a new data point, it compares it to the ones it memorized and finds the most similar ones to make a prediction. Think of classifying a new song by finding which songs in your existing playlists it sounds most like.
So it relies on similarity to known examples.
Exactly. Model-based learning, though, tries to build a general model from the training data. It looks for underlying patterns and relationships.
Like finding a trend line.
Yeah, like fitting a line to data showing, say, ad spend versus sales. Once you have that line, the model, you can predict sales for a new ad budget. So one memorizes and compares, the other builds a general rule or formula.
Got it. That's a clear distinction. Now, it seems like no matter which approach you use, the data itself is absolutely key, like garbage in, garbage out.
Oh, absolutely critical. The book emphasizes this, referencing that idea of the unreasonable effectiveness of data. Some early research showed that even simple algorithms could do surprisingly well on complex tasks if you just fed them massive amounts of data.
So more data is generally better.
Often, yes. But, and this is a huge but, the quality is just as vital, maybe more so. The book lists pitfalls. Not enough data, obviously, but also non-representative data or sampling
Like
bias.
the self-driving car only trained on sunny days.
Exactly. It won't work in the rain. Poor quality data errors, outliers, missing values that can mess things up badly, and irrelevant features, including data that doesn't actually help predict the target, can just confuse the model.
So you need enough good, relevant data.
Precisely. And that leads into what's called feature engineering. This is the whole process of selecting the best features, maybe transforming them, or even creating new, more informative features from the ones you have. It's really about crafting the best possible input for your model.
That sounds like where a lot of the domain knowledge and skill comes in. Okay, so we have good data, we've picked an algorithm. How do we make sure the model is learning the right things, not just memorizing the training set or being too simplistic? I'm thinking overfitting and underfitting.
Yeah, those are the two big failure modes you need to watch out for. Overfitting is when the model learns the training data too well. It captures not just the underlying patterns, but also the noise and random fluctuations specific to that data.
Like that taxi driver analogy in the book. One bad ride doesn't mean all drivers are bad.
Exactly. You've overgeneralized from noisy data. An overfit model rocks on the training data but falls apart on new, unseen data. It hasn't learned the real signal. The book talks about regularization as a way to fight this.
Regularization.
Yeah, it's a set of techniques that constrain the model during training, discouraging it from becoming too complex. Think of it like adding a penalty for complexity. These techniques often have hyperparameters you can tune to control how much regularization you apply.
Okay, so regularization tries to prevent the model from fitting the noise. What about underfitting?
Underfitting is the opposite problem. The model is too simple. It fails to capture the underlying structure even in the training data. It performs poorly everywhere.
Like trying to fit a straight line to data that's clearly curved.
Precisely. If your model isn't even doing well on the data it was trained on, that's a strong sign of underfitting. You might need a more powerful model, better features, or maybe you've regularized it too much. Looking at how performance changes on both training and a separate validation set during training can help diagnose these issues.
Right, finding that balance. Okay, so we've trained a model. We've tried to avoid overfitting and underfitting. How do we actually measure how good it is? What are the metrics?
Evaluation is key, and the metrics depend on the task. For regression predicting numbers, a common one is root mean square error, RMSE. It gives you a sense of the typical size of the model's prediction errors.
Makes sense for numbers. What about classification? Like, is it a cat or not?
Right. The simplest metric is accuracy. What percentage did it get right? But as the book points out with that Never 5 classifier example, accuracy can be really misleading, especially with unbalanced data sets.
Ah, yeah, the one where always guessing not 5 gives 90% accuracy if only 10% are 5s.
Exactly. Sounds great, but the model is useless. That's where precision and recall become crucial. Precision asks, when the model predicted yes, like this is a 5, how often was it correct?
Right.
And recall asks, of all the actual yes cases, all the real 5s, how many did the model find?
So precision is about the accuracy of positive predictions. Recall is about finding all the positives. Sounds like there might be a trade-off sometimes.
There almost always is. The book uses good examples. A Safe for Kids video detector probably wants super high precision. You really don't want to label unsafe videos as safe even if you miss a few. Lower recall might be acceptable.
Right, avoid false negatives there.
But a shoplifter detector, you might want high recall catch as many potential shoplifters as possible, even if it means more false alarms, lower precision.
Okay, that makes sense. Different priorities.
Exactly. And the F1 score is a way to combine precision and recall into a single number, giving you a balanced measure. It's the harmonic mean of the two.
Useful for seeing the overall balance. What about ROC curves and AUC? They sound a bit more complex.
The ROC curve receiver operating characteristic plots the true positive rate recall against the false positive rate as you vary the decision threshold of your classifier. The area under this curve, the AUC, gives a single score summarizing the model's ability to distinguish between classes across all thresholds. Higher AUC is generally better.
Okay.
However, the book makes a good point. When your positive class is rare, like finding rare diseases. Or if you care much more about false positives than false negatives, precision recall PR curves can often be more informative than ROC curves.
Right, because a small number of false positives can really tank your precision when the actual positives are rare.
Exactly. So choose your metric wisely based on the problem.
Okay, that's evaluation. Let's get into the mechanics. How do we actually train these models, like linear regression?
Right. Linear regression is often a starting point. You're trying to fit a straight line or a plane or hyperplane in higher dimensions to your data. The goal is to find the line parameters, the slope and intercept, that minimize the error between the line's predictions and the actual data points.
And how do we find that best line?
Often with an algorithm called gradient descent. The idea is you start with a random guess for the line's parameters, calculate how much error that line produces, and then nudge the parameters in the direction that reduces the error the most, like taking a step downhill on an error surface.
Okay, tiny steps downhill until you reach the bottom.
Pretty much. There are flavors. Batch gradient descent uses all the training data for each step, accurate but slow on big data sets. Stochastic gradient descent, SGD, uses just one random example per step, much faster, but the path downhill is noisier, more erratic.
It jumps around a bit.
Yeah. Mini-batch gradient descent is a compromise, uses a small random subset, a mini-batch, for each step. It's often the most practical. A key thing here is the learning rate. How big are those downhill steps?
Right, too big and you overshoot, too small and it takes forever.
Exactly. Finding a good learning rate is crucial. The book mentions SGD's randomness can help it escape shallow, local, minimal little dips that aren't the true lowest point, but it might not settle perfectly at the very bottom. That leads to the idea of a learning schedule, where you gradually decrease the learning rate as you get closer to the minimum.
Start fast, then get more careful. Makes sense. What if the relationship isn't linear? Polynomial regression.
Right. If your data has a curve, a straight line won't fit well. Polynomial regression adds powers of your features, like x squared, x cubed, to the model. This lets you fit curves.
More flexible.
Much more flexible, but you have to be careful. Use too high a degree polynomial, and you can easily overfit the curve wiggles too much to fit the noise in the training data.
Back to overfitting. So find the right amount of curve. Now, for classification, you mentioned logistic regression.
Yes, logistic regression is a workhorse for binary classification, yes, no, spam, not spam. It doesn't output a class directly, but rather the probability that an instance belongs to the positive class. It uses the logistic function, or sigmoid function, to squash the output between 0 and 1.
So it gives a probability, and you set a threshold like 0.5 to decide the class.
Exactly, and the decision boundary it creates is linear. For problems with more than two classes, there's a generalization called softmax regression, which calculates a probability for each class, all summing to 1.
Okay, so logistic for two classes, softmax for multiple.
Got it.
Now, support vector machines, SVMs. These sound powerful.
They can be very powerful, especially for classification with clear margins. The basic idea of a linear SVM is to find the line or hyperplane that separates the classes with the largest possible street or margin between them.
Widest possible gap between the classes.
Right. It focuses on the data points closest to the boundary, support vectors. This large margin approach often leads to good generalization. But real data is messy. It's often not perfectly separable by a line.
Yeah, what then?
That's where soft margin classification comes in. It allows some points to be within the margin or even on the wrong side, trading off a perfectly wide margin for better overall classification on noisy data. You control this trade-off with a hyperparameter.
A bit more tolerance for errors to get a better fit overall.
Precisely. And for data that's fundamentally nonlinear, SVMs have a really clever trick. The kernel trick.
The kernel trick. Sounds intriguing.
It is. Instead of actually adding complex polynomial features or mapping the data to a much higher dimension to make it linearly separable, which can be computationally crazy kernels, let you get the result of doing that without actually performing the transformation.
How?
They compute the relationships or similarities between data points as if they were in that higher dimensional space. Common kernels, like the polynomial kernel or the Gaussian RBF kernel, allow SVMs to find incredibly complex nonlinear decision boundaries efficiently. It's pretty neat.
That is clever. Less computation. Same powerful result. Okay, moving on to decision trees. These seem more intuitive, like a flowchart.
They are very intuitive. A decision tree asks a series of questions about the features to split the data, leading down branches to a final classification at a leaf node. Think of 20 questions. They can naturally capture complex, nonlinear patterns.
How does it decide which question to ask at each step?
It typically looks for the feature in the split point that results in the purest possible child nodes containing mostly instances of a single class. A common measure for this is Gini impurity. The goal is to reduce impurity as much as possible with each split.
Okay, make the groups as homogeneous as possible,
Yeah.
but you mentioned they can overfit.
Oh yeah, big time. If you let a tree grow deep enough, it can create rules that perfectly classify every single training instance, essentially memorizing the data, including noise. These overly complex trees don't generalize well.
So individual trees can be unstable. How do we fix that?
Ensemble methods. The idea is don't rely on one model, combine the predictions of many, wisdom of the crowd, basically. A simple approach is a voting classifier. Train different types of models, like an SVM, a logistic regression, a decision tree, on the same data, and take a majority vote for the final prediction.
Simple enough. What else?
Then you have methods like bagging and pasting. These train multiple instances of the same algorithm, often decision trees, on different random subsets of the training data.
Multiple trees, slightly different data for each.
Exactly. Bagging samples the data with replacement, so some data points might be picked multiple times for one tree, others not at all. Pasting samples without replacement. Since each tree sees a slightly different view of the data, their errors tend to be different. Averaging their predictions reduces variance and leads to a much more robust model. Random forests are a very popular example of bagging with the decision trees, adding an extra layer of randomness by also considering only a random subset of features at each split.
So random forest, many trees, plus random data subsets, plus random feature subsets. That sounds robust. What about boosting? That sounds different from bagging.
It is. Boosting also builds an ensemble, but it does it sequentially. Each new model tries to fix the errors made by the models before it.
Learning from mistakes.
Exactly. AdaBoost, adaptive boosting, is a classic example. It trains a predictor, then increases the relative weight of the training instances that the predictor got wrong. The next predictor then focuses more on these hard instances. The final prediction is a weighted combination of all the predictors.
Okay, focusing on the tough cases.
Then there's gradient boosting. It also trains models sequentially, but each new predictor is trained to fit the residual errors of the previous predictor, the difference between the actual values and the predictions so far. It's like each new model tries to predict what the ensemble is still getting wrong. It's very powerful, often uses trees, and has a learning rate parameter that shrinks the contribution of each tree to prevent overfitting.
So AdaBoost adjusts weights, gradient boosting fits residuals. Both are sequential improvements. Powerful stuff. Now, what about when we have tons and tons of features? High-dimensional data, that sounds like a problem.
It definitely can be. That's the curse of dimensionality. With lots of features, training can become very slow, the data becomes sparse, making patterns harder to find, and there's a much higher risk of overfitting because the model has so many ways to fit the training data.
So we want fewer dimensions, ideally. How do we reduce them?
Two main approaches: projection and manifold learning. Projection tries to find a lower dimensional flat surface or subspace that the data mostly lies on, and then projects the data onto it. Principal component analysis, PCA, is the most famous projection technique.
PCA. I've heard of that. How does it work?
PCA finds the axes, or principal components, along which the data has the most variance, the most spread. It then projects the data onto the first few principal components, capturing most of the information while discarding the dimensions with less variance. The book mentions it often uses singular value decomposition, SVD, to find these components efficiently.
Okay, so keep the directions where the data varies the most. What's manifold learning?
Manifold learning assumes the data lies on a lower dimensional manifold. Think of a rolled-up sheet of paper in 3D space. The manifold itself is 2D, but it exists in 3D. Manifold learning algorithms try to unroll this manifold to find the data's true, lower dimensional structure, even if it's curved. Techniques like LLE and ISOMAP do this.
More complex than projection, maybe, for twisty data.
Exactly. And just like SVMs, there's kernel PCA, which uses the kernel trick to perform nonlinear dimensionality reduction, essentially finding principal components in a higher dimensional feature space.
Okay, lots of ways to simplify complex data. Now, switching gears to unsupervised learning, again, clustering. Finding groups in unlabeled data.
Right. The goal is to group similar data points together without knowing the right groups beforehand. Useful for customer segmentation, finding topics in documents, image segmentation, lots of applications.
What's a common way to do it?
K-means is probably the most popular. It's pretty simple conceptually. You start by guessing K cluster centers, or centroids. Then you assign each data point to its nearest centroid. Then you update each centroid to be the mean of all the points assigned to it, and you repeat the assignment and update steps until the centroids stop moving much.
Assign, update, until stable. Sounds efficient.
It is generally quite efficient, but it assumes clusters are roughly spherical and equally sized, which isn't always true. Another approach is using Gaussian mixtures.
Gaussian mixtures.
Yeah, this assumes the data is generated from a mix of several Gaussian distributions, each representing a cluster. It's a probabilistic approach. It tries to find the parameters of these Gaussians using an algorithm called expectation maximization, EM. A nice thing is it gives you the probability that each point belongs to each cluster, not just a hard assignment.
More flexible for weirdly shaped clusters, maybe?
Right.
Okay, we absolutely have to talk about neural networks. ANs. They're everywhere now.
Absolutely. The foundation of modern deep learning. Chapter 10 starts with the perceptron, one of the earliest, simplest ANNs. It takes inputs, multiplies them by weights, sums them up, and applies a step function to make a binary decision. It learns by adjusting weights based on errors.
Simple but limited.
Very limited.
Yeah.
Can only learn linearly separable patterns. The big leap came with multi-layer perceptrons, MLPs. These have input layers, output layers, and one or more hidden layers in between. These hidden layers, combined with nonlinear activation functions applied to the neuron outputs, like sigmoid or more commonly now, RailU, allow MLPs to learn incredibly complex nonlinear patterns.
So hidden layers and activation functions are key to their power. How do they learn?
Through a process called backpropagation, usually combined with some form of gradient descent. Backpropagation calculates how much each connection weight in the network contributed to the final error, and gradient descent uses that information to adjust the weights slightly to reduce the error. It propagates the error signal backward through the network.
Okay, error flows back, weights get adjusted, and libraries like TensorFlow and Keras make this easier.
Massively easier. Chapter 12 covers this. TensorFlow provides the low-level computation engine, often optimized for GPUs. Keras is a high-level API that runs on top of TensorFlow and other backends, making it much simpler to define, train, and evaluate neural networks. Keras has things like the sequential API for simple stacks of layers, and the functional API for building more complex network architectures, like ones with multiple inputs or outputs.
They handle the heavy lifting.
Yeah.
What about tools to help during training? Callbacks?
Yeah, callbacks and Keras are super useful. They're functions you can have run at different stages of training. Like model checkpoint automatically saves your model periodically, maybe only saving the best version seen so far on a validation set. Early stopping monitors performance and stops training if it stops improving, preventing wasted time and potential overfitting. TensorBoard is another callback that lets you visualize training progress, network structure, and other metrics in your browser.
Very handy. Now, tuning these networks hyperparameters. Sounds like there are a lot of knobs to turn.
There are. It's a big part of getting good results. Chapter 11 dives into this. Finding the right learning rate for your optimizer is critical. Choosing the optimizer itself, SGD with momentum, Nesterov, Adagrod, Atom, they all have different characteristics. Batch size affects training speed and stability. Number of layers, number of neurons per layer. It's a lot. Often requires experimentation. Learning rate scheduling, like gradually reducing the rate, is also a common technique to improve convergence.
A lot to experiment with. What about common problems when training deep networks, ones with many layers?
Yeah, deep networks bring challenges. Vanishing gradients where the error signal gets weaker and weaker as it propagates backward, making early layers learn very slowly. Exploding gradients the opposite, where the signal gets too strong and weights fluctuate wildly.
How do we deal with those?
Batch normalization is a big one. It normalizes the inputs to each layer during training, which helps stabilize gradients, allows for higher learning rates, and acts as a regularizer. It's become almost standard practice. Regularization techniques like L1, L2, and especially dropout, randomly turning off neurons during training, are crucial to prevent overfitting in deep nets. Gradient clipping can cap the gradient values to prevent them from exploding.
Okay, batch norm and dropout sound key for deep learning. Let's move to specific network types. CNNs for images.
Convolutional neural networks,
Yeah.
Chapter 14, they're designed for grid-like data, especially images. The core idea is the convolutional layer. Instead of connecting every input pixel to every neuron in the first hidden layer, like in an MLP, a convolutional layer uses small filters or kernels that slide across the input image.
Filters, like edge detectors.
Exactly. These filters learn to detect specific local patterns, edges, corners, textures, simple shapes. Applying a filter across the image creates a feature map highlighting where that pattern occurs. CNNs typically stack these convolutional layers, often followed by pooling layers that downsample the feature maps, making them smaller and more robust to small variations, and then finally some fully connected layers for classification.
So layers learn simple features, then subsequent layers combine those into more complex ones.
Precisely. And transfer learning is huge here. You can take a CNN pre-trained on a massive dataset like ImageNet, chop off its final classification layer, and then fine-tune it on your own smaller dataset. Works incredibly well. CNNs are also the basis for object detection, finding and classifying objects, and semantic segmentation, labeling every pixel in an image.
Powerful stuff for vision. What about sequences? Text, time series.
Yeah.
That's our NNS, right?
Recurrent neural networks, yes. Chapter 15. RNNs are designed for sequential data. They have loops, allowing information from previous steps in the sequence to persist and influence the processing of the current step. They have a sort of memory.
So they can remember what came earlier in the sentence, for example.
That's the idea. They can be used for sequence-to-vector tasks like sentiment analysis, read a sentence, output positive and negative, vector to sequence, input an idea, output a sentence, and sequence-to-sequence like machine translation, input English sentence, output French sentence.
But didn't you say deep networks have gradient problems? RNNs processing long sequences must struggle.
They do. Standard RNNs struggle with long-range dependencies due to vanishing exploding gradients. That's why LSTM, long short-term memory, and GRU, gated recurrent unit cells, were invented. They have internal gates that control the flow of information, allowing them to selectively remember or forget information over much longer sequences. They're much better at capturing long-term patterns.
LSTMs and GRUs have better memory management.
Essentially, yes. The book also mentions using 1D convolutions for sequences, and NMT, neural machine translation, often uses encoder-decoder architectures, sometimes with attention mechanisms that let the decoder focus on relevant parts of the input sequence when generating output. And then Chapter 16 introduces transformers.
Transformers, they're huge now, right? BERT, GPT.
Exactly. Transformers have largely replaced RNNs for many state-of-the-art NLP tasks. They rely heavily on self-attention mechanisms, which allow the model to weigh the importance of different words in the input sequence when processing a particular word, regardless of their distance. This parallel processing of the sequence makes them very efficient to train on large datasets.
So attention lets them connect related words even if they're far apart. Okay, briefly, what about networks that generate stuff? Autoencoders and GANs.
Right, Chapter 17. Autoencoders are unsupervised networks trained to reconstruct their input. They typically have a bottleneck layer in the middle, forcing them to learn a compressed representation or encoding of the data, useful for dimensionality reduction, anomaly detection, or pre-training other networks. There are variations like sparse, denoising, and variational autoencoders, VAEs.
Learn a compact code for the data. What about GANs? Generative adversarial networks.
GANs are fascinating. You have two networks competing. A generator tries to create fake data, like images, that looks real, and a discriminator tries to tell the difference between real data and the fake data from the generator.
A forger and a detective.
Exactly. They train together. The generator gets better at fooling the discriminator, and the discriminator gets better at spotting fakes. This pushes the generator to create incredibly realistic outputs. DC GANs, deep convolutional GANs, use CNNs in their structure and are great at generating images.
Amazing they can learn to generate realistic things through competition. Okay, last big topic area. Reinforcement learning revisited, and then deployment.
Chapter 18 goes deeper into RL. We mentioned the agent, environment, rewards. Policy gradient methods try to directly learn the policy function, state action probabilities, by adjusting it based on the rewards received. Q-learning, on the other hand, learns a Q-value function, which estimates the expected future reward of taking a certain action in a certain state. Deep Q networks, DQNs, use deep neural networks to approximate these Q values for complex environments. Libraries like TF agents help implement these.
So different strategies for learning the best actions, and finally, Chapter 19, putting these models into production.
Right. Training is one thing, deploying is another. TensorFlow Serving is a system designed specifically for serving trained models. It can handle multiple model versions, batch incoming requests for efficiency, and expose models via standard web APIs like REST or the more efficient gRPC.
Making the model accessible.
Exactly. Cloud platforms like Google Cloud AI Platform offer infrastructure for both training, like powerful VMs with GPUs, and deployment. And TensorFlow itself has tools like mirrored strategy for distributing training across multiple GPUs on a single machine or even multiple machines, speeding up the training of large models significantly.
So tools exist for the whole life cycle, from training huge models to serving them reliably. Wow. Okay, we have covered a ton of ground here.
We really have, from the absolute basics of what ML is through supervised and unsupervised methods, evaluation, trees, SVMs, ensembles, deep learning with ANNs, CNNs, RNNs, transformers, generative models, RL, and deployment. It's a whirlwind tour.
Yeah, and it's crucial to remember this is just scratching the surface, right? This field is huge and moves incredibly fast.
Absolutely. But hopefully this gives you, the listener, a solid framework.
That was the goal, to hit the key concepts, the main techniques, give you that foundational understanding without, drowning you in equations.
And having this base understanding really empowers you to then dive deeper into specific